houses that get 1. Cruck frame construction, the flexible fortress. When we build today, we aim for rigid strength. Medieval builders understood something more profound, the power of controlled flexibility. The cruck frame wasn't just a building technique. It was a complete rethinking of how structures respond to wind and weather. Using massive, curved timbers harvested from specially selected trees, these frames created an unbroken arch from ground to roof peak. Unlike modern post and beam construction with its many joints and connection points, the cruck frame distributed force along continuous curves. During violent storms, these structures would flex slightly, absorbing and dispersing wind energy rather than resisting it. The building literally moved with the storm instead of fighting against it. Some cruck frames were designed to allow up to 4 inches of movement during extreme winds without compromising structural integrity. The genius was in the selection of materials. Builders didn't use just any trees. They sought out naturally curved oak or elm that had grown under specific conditions. The grain of these timbers followed the curve, creating natural strength that couldn't be replicated by cutting straight lumber into curved shapes. Some builders would even identify promising trees decades before harvest, gradually training them to grow in the desired curve. The most sophisticated cruck frames incorporated different wood types for different functions: flexible woods where movement was needed, dense hardwoods where stability was required. The result was a structure that could bend without breaking through centuries of storms. What makes this technique remarkable isn't just that it worked 800 years ago. It's that some of these buildings are still standing today, having survived hundreds of hurricanes and windstorms that have destroyed newer structures around them. For modern homeowners who replace roofs every 20-30 years after storm damage, this medieval approach offers something profound. Structures designed to work with nature's forces rather than futilely opposing them. 2. Turf integration, living armor against elements. Today's buildings fight against nature with synthetic barriers. Medieval builders created something far more ingenious: shelters that used living materials as their shield, a technique that modern green architecture is only beginning to rediscover. Turf integration wasn't simply placing sod on a roof. It was a sophisticated multi-layer system that transformed ordinary structures into weather-resistant fortresses. The process began with a waterproof base layer of birch bark or thin slate. Above this, builders placed a carefully selected mixture of soil, clay, and specific plant species chosen for their root structures and water management properties. Unlike modern green roofs that require irrigation and maintenance, medieval turf systems were self-regulating ecosystems. The plants selected would naturally maintain the optimal moisture level, absorbing excess during rainstorms and retaining critical moisture during dry periods. The dense root networks created a living mesh that held the entire system together through high winds. During winter storms, these living roofs provided remarkable insulation. The soil layer would freeze, creating a solid barrier against heat loss, while the air pockets within the turf layer provided additional insulation. In summer, the same system absorbed solar radiation that would otherwise overheat the structure. The most sophisticated versions included specific herbs and mosses that naturally repelled insects and prevented rot in the underlying timbers. Some Scandinavian examples incorporated selective plant species that would change color to indicate when maintenance was needed. A medieval early warning system. These living roofs could last for decades with minimal maintenance, sometimes outliving the original builders. The entire system would evolve over time, becoming more resilient as the plant community established itself. What makes this approach remarkable isn't just its effectiveness against storms, it's the regenerative nature of the protection, a defensive system that actually strengthens itself over time instead of degrading like modern materials. For contemporary homeowners who replace storm-damaged shingles and siding after severe weather, this medieval technique offers a profound alternative, protection that grows stronger, not weaker, with each passing season. 3. Wattle and daub, the flexible impact absorber. Before drywall, fiberglass, and spray foam insulation, medieval builders developed a wall system so effective against storms that examples still stand after 700 years. A technique that combined flexibility and strength in ways modern construction has largely abandoned. Wattle and daub wasn't just primitive plastering, it was an engineered composite material that created walls with remarkable properties. The process began with the wattle, a woven lattice of thin, flexible branches, usually hazel, oak, or willow, creating a matrix similar to modern rebar but with crucial differences. Unlike rigid modern wall systems, the wattle framework had calculated flexibility. During high winds or even earthquakes, these walls could flex slightly without cracking. The woven pattern distributed force across the entire wall rather than concentrating it at rigid connection points. The daub, a mixture of clay, sand, animal dung, and fibrous materials like straw or animal hair, wasn't simply applied as a covering. It was worked into and through the wattle framework, creating a true composite where each material compensated for the weaknesses of the other. The clay mixture provided mass and insulation, while the fibrous materials prevented cracking and added tensile strength. The most sophisticated versions used multiple layers with different compositions. The base layer focused on adhesion to the wattle, middle layers provided mass and insulation, and the final layer was formulated for weather resistance and sometimes incorporated lime for water repellency and natural antimicrobial properties. During storms, these walls performed remarkably. They absorbed impact from flying debris without shattering like modern drywall. They dampened sound, reducing the psychological stress of howling winds. They regulated humidity, preventing the internal condensation that plagues many modern homes during weather changes. What makes this system extraordinary isn't just its storm resistance, it's the repairability. Damage from severe weather could be quickly fixed using readily available materials, no specialized components or tools required. Some medieval communities could repair an entire damaged wall section in a single day. For modern homeowners who face costly repairs after storms damage vinyl siding or crack drywall, this medieval technology offers something remarkable. Walls that bend rather than break, and when damaged, can be repaired with materials you could gather from your own property. 4. Thatch engineering, the hydrophobic roof system. We often think of thatched roofs as primitive and vulnerable, but medieval thatchers created roofing systems with water-repelling properties that modern materials still struggle to match without a single synthetic component. Medieval thatch wasn't just piled plant material. It was a precisely engineered system with sophisticated water management built into its very structure. The process began with material selection. Not just any straw or reed would suffice. Water reed, wheat straw, or rye straw were chosen based on local climate conditions, each with different properties for different challenges. The genius was in the installation technique. Each bundle was placed at specific angles that maximized water shedding while minimizing wind resistance. The bundles weren't simply tied down. They were stitched through with complex patterns that distributed wind force across the entire roof surface. Some advanced techniques used multiple layers with different densities. Denser outer layers for weather protection and looser inner layers for insulation. During heavy rainstorms, properly constructed thatch performed remarkably. The outer layer would shed water while the dense packing prevented any penetration. The natural silica content in materials like water reed created a hydrophobic surface that actually improved with age as the silica content became more concentrated at the surface. In high winds, thatch had a crucial advantage over modern materials. It was both strong and light. While heavy modern roofing can be torn off when wind gets underneath it, The lightweight nature of thatch meant less leverage for the wind to exploit. The stitching patterns were specifically designed to prevent the wind from getting under the edges, a problem that regularly defeats modern shingles. The most sophisticated thatch systems included built-in ventilation channels that prevented condensation, a common failure point in modern roofs. Some regional variations incorporated natural fungicides like certain ferns layered into the thatch to prevent rot and extend lifespan. What makes medieval thatch extraordinary isn't just its effectiveness, it's the longevity. A properly constructed thatched roof could last 40-60 years with minimal maintenance, outlasting many modern roofing materials while performing better in extreme weather. For today's homeowners who replace storm-damaged asphalt shingles every 15 to 20 years, this medieval technology offers something remarkable: a roof system that actually performs better during its second and third decades than when first installed. 5. Dry stone construction, the self-healing barrier. Before concrete foundations and mortared walls, medieval builders perfected a construction technique so resilient it could withstand flooding, ground shifts, and freezing conditions while actually repairing itself during storms. Dry stone construction wasn't simply piling rocks. It was a sophisticated engineering system that created structures with remarkable properties. Using no mortar or binding agents, these walls and foundations relied entirely on precise stone selection, strategic placement, and the physics of friction and gravity. The genius was in the deliberate incorporation of controlled movement. Unlike rigid modern concrete that cracks when the ground shifts, dry stone structures were designed to move slightly, settling back into stable positions. During floods or ground heaving from freeze-thaw cycles, these structures would shift minutely and then resettle, effectively healing themselves. The construction technique required profound understanding of stone properties. Builders selected stones not just for size, but for their friction coefficients and weathering characteristics. The pattern of placement distributed weight and force along predictable paths, creating structures that actually strengthened under pressure rather than weakening. During severe storms, these structures demonstrated remarkable resilience. Floodwaters could flow through the tiny gaps between stones without undermining the structure. Frost could expand in these same gaps without cracking the material. Wind would find no large surface to push against, passing through the small openings while the mass of the stone remained unmoved. The most sophisticated examples included specific drainage patterns built into the structure itself. Some designs incorporated graduated stone sizes that naturally filtered water while maintaining structural integrity, a medieval version of modern drainage engineering. What makes this approach extraordinary isn't just its effectiveness against individual storms, it's the cumulative resilience. Many dry stone structures have stood for 500+ years through thousands of severe weather events that have destroyed countless modern structures around them. For contemporary builders who pour concrete foundations that crack after just a few freeze-thaw cycles, this medieval technology offers something profound: structures that work with natural forces rather than futilely resisting them, becoming stronger, not weaker, with each passing year. 6. Smoke hardening, the invisible shield. Before chemical preservatives and synthetic coatings, medieval builders developed a sophisticated weatherproofing system that transformed ordinary wood into storm-resistant material, using nothing but carefully controlled smoke. Smoke hardening wasn't simply drying wood near fire. It was a precise process that fundamentally altered the cellular structure of timber. The technique began with green wood selected for specific structural purposes. Rather than simply drying it, builders would expose these timbers to specific types of smoke in controlled environments for weeks or even months. The genius was in understanding smoke chemistry before chemistry even existed as a science. Different wood sources for the smoke produced different effects. Resinous woods like pine created water-resistant compounds that penetrated the timber. Hardwoods like oak produced smoke that densified the surface and increased hardness. Some techniques even use specific mineral-rich materials added to the fire to create smoke with additional protective properties. The process didn't just dry the wood, it transformed it. The compounds in the smoke would react with the natural resins and cellulose in the timber, creating new molecular structures more resistant to water, insects, and decay. The smoke particles would fill the microscopic pores in the wood, creating a barrier against moisture while still allowing the timber to breathe. During storms, smoke-hardened wood performed remarkably. It resisted warping from humidity changes. It maintained structural integrity when wet. It dried quickly after exposure to water without the cracking and checking that plague modern lumber. The most sophisticated versions of this technique created timber with different properties at different depths, a water-resistant exterior surrounding a flexible core. Some regional variations produced timbers that would actually darken and harden further when exposed to rain, essentially improving their protective qualities with each storm. What makes this approach extraordinary isn't just its effectiveness, it's the transformation of a vulnerability into a strength. Instead of fighting against wood's natural tendency to interact with moisture, this technique worked with these properties to create a material that responded beneficially to the very conditions that normally cause decay. For modern homeowners who replace rot-damaged wood every few years, this medieval technology offers something remarkable: timber that not only resists storms but potentially improves with each exposure without a single chemical preservative. 7. Passive ventilation networks, the invisible air manager. Before HVAC systems and electric fans, medieval builders created sophisticated air management systems that prevented storm damage while maintaining comfort, using nothing but architectural design and an understanding of physics. Medieval passive ventilation wasn't just random roof holes. It was an integrated network of strategically placed openings, channels, and chambers that controlled air movement throughout the structure. The system began with understanding prevailing wind patterns and seasonal variations specific to each building site. The genius was in creating a self-regulating system that responded to external conditions without any moving parts or controls. During storms, these ventilation networks prevented the pressure differentials that often damage modern buildings. When high winds create low pressure above a modern roof, the higher pressure inside can literally push the roof upward. Medieval ventilation systems automatically equalized these pressures. The design incorporated multiple elements working together. Low inlet vents and high outlet vents created natural convection currents. Narrowing channels accelerated or slowed air movement based on Bernoulli principles. Thermal masses stored and released heat to drive air circulation when wind was absent. During severe weather, these systems demonstrated remarkable functionality. They prevented the moisture buildup that leads to mold and rot in modern sealed buildings. They reduced structural stress from wind pressure. They maintained air quality even when occupants couldn't open windows or doors. The most sophisticated examples included seasonal adjustment features, openings that could be reconfigured for summer cooling or winter heat retention. Some incorporated filtering elements like water features that would clean and humidify air during dry conditions or remove moisture during humid periods. What makes this approach extraordinary isn't just its effectiveness during storms. It's the complete elimination of dependency. These systems required no power, no replacement parts, and minimal maintenance, continuing to function through centuries of use. For modern homeowners who lose ventilation when storms knock out power, this medieval technology offers something profound: climate management that never fails, never needs replacement, and works better during emergencies than under normal conditions. The forgotten wisdom. We often view medieval construction as primitive and limited. Medieval builders didn't just create structures. They developed integrated systems that worked with available materials and natural processes. They didn't fight against environmental forces. They designed with them. Every technique we've explored reflects a deeper understanding of resilience that modern construction has often sacrificed for convenience or cost. They didn't separate the building from its environment or its occupants. Each structure was part of a larger system that included the landscape, climate patterns, and human behaviors. This wasn't primitive limitation. It was sophisticated systems thinking centuries before we had a name for it. Today, we've traded resilience for convenience. We've exchanged adaptability for standardization. We've replaced regenerative materials with disposable ones. And in doing so, we've created shelters that often fail precisely when we need them most, during severe weather. The most powerful medieval shelter innovation wasn't any specific technique. It was their integrated approach to resilience. Nothing was designed in isolation. Everything had multiple functions. Systems worked together rather than competing. This wasn't primitive necessity. It was brilliant design that modern architecture is only beginning to rediscover. Here's the reality nobody wants to admit. We spend fortunes on gear that fails exactly when we need it most, while primitive people created solutions that have worked for 800 years and counting. Houses that strengthen during storms. Systems that fish by themselves while you sleep. Tools that do 10 things and never break. The question is no longer, does this really work? The question is, why did we abandon superior technology for inferior convenience? Now, while modern fishermen spend thousands on equipment and come home empty-handed, medieval communities built a single installation that captured 10,000 fish per night, automatically, without human supervision. How? They hacked nature itself. And no, I'm not exaggerating. Archaeological records prove these numbers. Let's reveal 5 medieval fishing systems that are pure genius in disguise. While modern fishermen struggle to catch a few fish with expensive gear, medieval communities could harvest thousands using only sticks, stones, and plants. They built massive underwater fish-trapping cities, turned darkness into their greatest weapon, and even weaponized plants to harvest entire rivers. These 5 genius techniques could feed hundreds for months using nothing but materials they could find, make, or grow themselves. Weir. Fishing. Medieval communities didn't just catch fish, they built massive underwater cities designed to trap thousands of fish with every tide cycle. Weir fishing represented medieval engineering at its most ambitious, creating permanent fishing installations that could feed entire regions without daily maintenance. Archaeological evidence from the Blackwater estuary in Essex reveals the staggering scale of medieval weir systems, over 13,000 timber posts arranged in complex patterns stretching half a mile into the sea. These weren't simple fences. They were sophisticated fish-directing systems that had been refined through centuries of experimentation and represented some of the largest construction projects of their era. The engineering principles behind weir fishing demonstrated remarkable understanding of fish behavior and water dynamics. Medieval builders positioned these structures in tidal estuaries and river mouths, where migrating fish naturally traveled, then used the fish's own instincts against them. Rather than trying to catch fish randomly, weirs created predictable gathering points where communities could harvest fish with minimal effort. Construction required enormous community investment and cooperation. Building a single weir system demanded hundreds of workers, thousands of wooden posts, and months of coordinated effort. Communities had to organize timber harvesting, post sharpening, transportation to construction sites, and synchronized installation during specific tidal conditions. This represented medieval project management at its most complex. The wooden framework created a funnel system that guided fish toward increasingly narrow passages. As fish followed what appeared to be natural underwater channels, they found themselves directed into woven wicker collection areas where escape became impossible. The genius lay in making the trap feel like a natural path rather than an obvious barrier. Different weir designs targeted specific fish species and seasonal patterns. Salmon weirs operated differently from eel weirs, which required different approaches than general-purpose fish traps. Medieval communities developed specialized knowledge about which fish species could be caught when, allowing them to modify their weir configurations throughout the year for maximum effectiveness. Maintenance demanded constant attention and seasonal rebuilding. Winter storms, flooding, and normal wear required weir operators to replace damaged sections, clear debris, and rebuild entire sections. This created year-round employment for specialized weir-wrights, who possessed the technical knowledge necessary to maintain these complex systems. The productivity of successful weir systems was legendary. Historical records describe single weir operations producing thousands of fish during peak migration periods, providing enough protein to sustain large communities through entire seasons. These installations represented medieval industrial fishing at its most efficient. Legal frameworks developed around weir ownership and operation rights. Because successful weirs could control entire river systems, medieval laws strictly regulated who could build them, where they could be constructed, and how they should be operated. Weir rights became valuable property that could be inherited, sold, or disputed in medieval courts. Economic impact extended far beyond simple fish production. Successful weir operations supported entire industries: boat building, net making, fish processing, salt production for preservation, and transportation networks to distribute catch to inland communities. A single productive weir could anchor the economy of an entire region. Modern fisheries management still studies medieval weir systems for insights into sustainable fish harvesting. These installations worked with natural fish migration patterns rather than against them, often increasing fish populations through controlled harvesting that prevented overcrowding and disease outbreaks in fish populations. Torch spearing. When darkness fell over medieval waters, most fishermen returned to shore, but the most successful hunters were just beginning their work. Torch spearing, known as lestring in Norwegian and lystring in English, transformed night into the medieval fisherman's greatest advantage, utilizing fish behavior that daylight fishing could never exploit. The technique relied on a fundamental understanding of fish vision and behavior that modern science has confirmed. Fish become temporarily blinded and disoriented when exposed to bright light in dark water. Medieval fishermen discovered this weakness and built an entire hunting system around exploiting it, turning their prey's own nervous system against them. Equipment was remarkably simple yet effective. The fishing spear featured multiple barbed prongs designed to prevent fish from sliding off after being struck. Unlike modern harpoons, medieval lysters used 3 to 5 prongs arranged to increase hit probability while ensuring that fish remained secured throughout the capture process. Torch technology determined success or failure of the entire operation. Medieval fishermen experimented with different materials to create torches that burned hot and bright while remaining waterproof enough to function during the inevitable splashing and humidity of nighttime fishing. Pine pitch, birch bark, and oil-soaked cloth created torches that could burn for hours. The hunting process required incredible skill and patience. Fishermen moved slowly through shallow water, holding torches high enough to illuminate underwater areas, while positioning spears for accurate strikes. The combination of balancing light, maintaining stealth, and executing precise spear throws demanded years of practice to master effectively. Boat-based torch spearing represented the advanced version of this technique. Medieval fishermen developed specialized boats designed for stability during spear fishing, with designated positions for torch holders and spear throwers. Successful teams could cover larger areas and access deeper waters where bigger fish congregated. Refraction presented the greatest technical challenge for torch spearing practitioners. Water bends light, making fish appear in different positions than their actual locations. Medieval fishermen had to learn compensation techniques, aiming below and slightly to one side of where fish appeared to ensure accurate strikes. Seasonal timing maximized torch spearing effectiveness. Medieval practitioners understood that certain fish species were more active during specific times of year, weather conditions, and lunar cycles. This knowledge allowed them to time their expeditions for maximum productivity rather than relying on random luck. Target species varied based on regional waters and seasonal availability. Salmon, trout, pike, and even eels could be taken using torch spearing techniques. Each species required slightly different approaches, spear modifications, and hunting strategies that experienced practitioners developed through extensive trial and error. Community cooperation enhanced individual success rates. Multiple fishermen working together could surround fish, drive them toward designated hunters, and coordinate strikes for maximum effectiveness. This teamwork transformed torch spearing from individual hunting into organized community food production. Legal restrictions eventually limited torch spearing in many regions. Medieval authorities recognized that the technique was so effective it could potentially deplete fish populations if used without regulation. Laws began restricting when, where, and how torch spearing could be practiced. Modern conservation efforts have largely banned torch spearing due to its effectiveness and potential for overfishing. However, the technique remains legal in some regions under strict regulations, and survival training programs still teach torch spearing as an emergency food procurement method. Willow basket traps. Medieval communities discovered that the most effective fishing gear grew directly from their own wetlands. Willow basket traps represented the perfect marriage of available materials and sophisticated engineering, creating fish-catching devices that could be manufactured entirely from resources found within walking distance of any village. The construction process began 3 years before a single fish was caught. Medieval trap makers cultivated willow beds specifically for fishing equipment, understanding that young willow shoots lack the strength and flexibility necessary for reliable trap construction. Only willow withies that had grown for at least 3 years possessed the proper balance of strength and bendability. Harvesting required precise timing and technique. Medieval craftsmen cut willow during late winter dormancy when sap levels were lowest, ensuring maximum durability and resistance to water damage. They selected shoots of specific diameters for different trap components, with thicker withies forming structural frameworks and thinner materials creating tight weaving patterns. Processing prepared raw willow for trap construction. Brown withies retain their bark for maximum strength and natural waterproofing. White withies had bark stripped away for flexibility. Buff withies were boiled with bark intact, then stripped, creating materials with intermediate properties. Medieval trap makers chose specific types based on intended use and performance requirements. Two-chambered design represented the height of medieval trap engineering sophistication. The large opening funnel guided fish into the main basket chamber, while a second internal chamber prevented escape once fish had entered. This double-trap system dramatically improved catch rates compared to simple single-chamber designs. Weaving techniques created traps that could withstand powerful river currents while maintaining precise mesh sizes. Medieval craftsmen developed specific weaving patterns that prevented small fish from escaping while allowing water to flow freely through the trap. The skill required to create these patterns was passed down through generations of specialist trap makers. Trap deployment required understanding of fish behavior and water dynamics. Medieval fishermen positioned basket traps in flowing rivers and tidal estuaries where fish naturally traveled, often creating temporary dams or guides to direct fish toward trap openings. Successful trap placement could determine the difference between feast and famine. Size specifications reflected practical transportation and handling constraints. 5-foot trap lengths represented the maximum size that individual fishermen could deploy, retrieve, and transport without assistance. This standardization allowed trap-making techniques to spread across different regions and fishing communities. Species-specific modifications optimized traps for different fishing targets. Eel traps used tighter weaving and different entry configurations than salmon traps. Trout traps required different positioning and handling than traps designed for bottom-feeding fish. Medieval communities developed specialized trap variants for their local fish populations. Maintenance schedules extended trap working life and ensured consistent performance. Medieval fishermen regularly inspected, repaired, and retreated their willow traps to prevent deterioration and maintain effectiveness. Proper maintenance could extend trap life for multiple fishing seasons, making the initial construction investment economically viable. Economic value created entire specialized industries around trap making and maintenance. Skilled trap makers became essential community members, often trading their services for food, shelter, and other necessities. The knowledge and skill required to make effective traps represented valuable intellectual property that communities carefully protected. Archaeological evidence reveals the widespread use of willow basket traps across medieval Europe. Trap fragments found at medieval sites indicate standardized construction techniques and suggest extensive trade networks for trap-making knowledge and materials. These discoveries confirm that basket trap fishing represented a major component of medieval food production systems. Longline tidal fishing. Medieval communities transformed the predictable rhythm of ocean tides into automated fishing systems that worked continuously without human supervision. The construction process began with massive rope-making operations that could take entire communities weeks to complete. Creating the main line required splicing together hundreds of shorter rope segments using hemp or flax cordage. Medieval fishermen learned specific knots and splicing techniques that prevented lines from breaking under the stress of strong currents and heavy fish loads. A single long line could stretch for miles, requiring enormous quantities of locally produced rope. The setup process began at low tide, when fishermen could wade into exposed areas to position anchor points. They drove wooden stakes deep into the seabed, or positioned heavy stone anchors at precise intervals, spacing them to create a grid pattern that covered maximum fishing area. Each anchor point had to be marked with floating indicators that could be seen during high tide. Hook attachment followed systematic patterns that medieval fishermen developed through generations of experimentation. Hooks were tied directly to the main line using specific spacing, typically every 3 to 6 feet, depending on target fish species and local conditions. Each hook required individual baiting, creating hours of preparation work before lines could be deployed. Bait preparation consumed enormous amounts of time and resources. Medieval communities dedicated groups of people to collecting shellfish, digging worms, catching small fish, and preparing other baits needed for hundreds of hooks. Bait had to be fresh enough to attract fish, but secure enough to stay attached through tidal cycles. Deployment timing required precise coordination with tidal schedules. Fishermen had narrow windows during low tide to set lines, attach final anchor points, and ensure proper positioning before waters rose. Missing these timing windows meant losing entire setup efforts and waiting for the next tidal cycle. Retrieval operations began at the following low tide, typically 12 hours later. Medieval fishermen worked systematically along their long lines, removing caught fish, checking hook conditions, and rebaiting hooks for the next cycle. Fish had to be processed immediately to prevent spoilage during the walk back to shore. Line maintenance represented ongoing work that determined longline fishing success rates. Medieval fishermen constantly repaired damaged sections, replaced broken hooks, reinforced anchor points, and adjusted line positioning based on seasonal changes in fish behavior and water conditions. Multiple line management allowed experienced practitioners to operate dozens of separate long lines simultaneously. Each line targeted different areas, depths, and fish species, creating diversified fishing operations that reduced risk and maximized total food production for their communities. Plant stunning. Medieval communities discovered they could weaponize the natural world itself by grinding specific plants into fish-stunning agents that transformed entire river systems into massive collection areas. The preparation process began with plant identification and cultivation that required specialized botanical knowledge passed down through generations. Root collection started during specific seasons when active compounds reached peak concentrations. Medieval practitioners learned that barbasco roots contained maximum stunning power when harvested during dry seasons, while other plants required different timing. They would carefully dig roots without killing parent plants, ensuring sustainable harvesting for future seasons. Processing techniques transformed raw plant materials into effective stunning agents through systematic preparation methods. Medieval fishermen crushed fresh roots using wooden mallets and stone grinding surfaces, breaking down plant fibers to release concentrated chemical compounds. The grinding process could take hours of intensive physical labor to prepare enough material for large-scale stunning operations. Paste preparation involved mixing ground plant materials with specific amounts of water to create thick, sticky pastes that would disperse properly in flowing water. Medieval practitioners learned exact water-to-plant ratios through trial and error, understanding that too much water diluted effectiveness, while too little prevented proper distribution. Stream preparation required coordinating community work teams to modify water flow before stunning operations began. Medieval fishermen built temporary dams using stones, logs, and mud to slow water movement in target areas. These modifications concentrated stunning agents and prevented them from being washed away before affecting fish populations. Application methods involve strategic placement of prepared plant materials upstream from target fishing areas. Medieval teams would position baskets filled with plant paste at specific intervals across stream width, ensuring even distribution as currents carried stunning agents downstream toward waiting fish populations. Timing coordination was crucial for successful stunning operations. Medieval practitioners learned to introduce plant materials during peak fish activity periods, typically during spawning migrations or seasonal feeding times when target fish species concentrated in predictable locations within river systems. Collection techniques had to match the dramatic productivity of plant stunning operations. When applications worked effectively, hundreds of stunned fish would surface simultaneously across large river areas. Medieval communities organized coordinated collection efforts using boats, hand nets, woven baskets, and large groups of people working together to gather floating fish before they recovered. Dosage control prevented permanent harm to fish populations while ensuring effective stunning results. Medieval practitioners developed techniques for judging proper plant quantities based on water volume, current speed, and target fish species. Too little stunning agent produced poor results, while excessive amounts could kill fish permanently. Recovery monitoring ensured sustainable fishing practices that preserved fish populations for future harvesting. Medieval communities learned that properly stunned fish recovered completely within hours when washed into untainted water, allowing fish populations to maintain healthy numbers despite regular stunning operations. Safety protocols protected human health during stunning operations and fish consumption. Although stunned fish remained perfectly safe for human consumption, medieval practitioners learned to avoid direct contact with concentrated plant preparations that could cause skin irritation or other health problems during preparation and application phases. These 5 medieval fishing techniques reveal the remarkable ingenuity of communities facing life or death challenges with nothing but natural materials and human creativity. From massive weir installations that could trap thousands of fish per tide to plant-based, stunning operations that could harvest entire river systems, medieval fishermen developed solutions that modern technology still struggles to match. What makes these techniques truly genius isn't just their effectiveness. It's how they solved complex engineering problems using only resources that communities could produce and control themselves. No supply chains, no industrial manufacturing, no external dependencies, just deep understanding of natural systems and generations of accumulated wisdom. The scale of these operations supported entire civilizations. Medieval fishing provided the protein foundation that enabled cities to grow and complex societies to develop. These weren't survival techniques. They were sophisticated food production systems that could feed thousands year-round. Modern fishing has gained convenience but lost much of the sustainability and resource efficiency that characterized medieval techniques. These methods worked with natural systems rather than against them, often increasing fish populations through controlled harvesting. The knowledge required to implement these techniques represented valuable intellectual property that communities carefully guarded. Master fishermen were respected community members whose expertise could determine survival during difficult times. These forgotten techniques offer modern communities valuable lessons about resource efficiency, sustainability, and local food production. As global supply chains become increasingly fragile, medieval fishing wisdom provides tested alternatives that worked for centuries. If you found these forgotten fishing techniques fascinating, there's an entire world of medieval survival wisdom waiting to be rediscovered. Subscribe to explore more ingenious solutions that sustained our ancestors. All right, moment of truth. You have indestructible shelter and guaranteed food. But what if I showed you a simple medieval map that works perfectly after being completely submerged in water? Or a common candle that's actually a 3-in-1 survival kit? Medieval people didn't carry tools. They carried ingenious systems disguised as everyday objects. Each item had at least 3 secret functions. Let's decode 7 medieval tools that will blow your mind. 1. Portable sundial. Today, we panic when our phone battery dies and we can't check the time. Medieval travelers simply looked to the sky. The portable sundial wasn't just a miniature version of those large garden ornaments. It was a sophisticated astronomical instrument that combined mathematics, astronomy, and craftsmanship into a device that provided surprisingly accurate time anywhere without ever needing power. Using carefully calibrated adjustable elements, these pocket-sized instruments could be tuned to different latitudes and seasons. Unlike our modern devices that become useless paperweights when batteries die, these medieval timekeepers operated on the one power source guaranteed never to fail: the sun itself. The genius wasn't just in telling time, it was in the adaptability. Fixed sundials only work in one location, but portable versions featured adjustable gnomons, the shadow casting element that could be set to the correct angle for the user's latitude. Some sophisticated models included small tables engraved directly on the instrument, showing the necessary adjustments for different regions and times of year. Historical accounts describe travelers using these devices to coordinate meetings, time religious observances, and navigate by maintaining awareness of time past. The most basic versions could tell time within 15 minutes, more than accurate enough for practical daily use in an era not obsessed with split-second scheduling. Medieval travelers often carried specialized compasses alongside their sundials to ensure proper orientation. The two instruments worked together as a system, the compass providing accurate alignment, and the sundial converting that alignment into time measurement. Some advanced designs integrated both functions into a single instrument that could tell time and direction simultaneously. The most sophisticated versions incorporated multiple functions beyond simple timekeeping. Some could determine the date, track seasonal changes, or even provide navigational information based on the sun's position. The finest examples were true multi-tools that combine timekeeping with other necessary functions in a single pocket-sized instrument. For modern outdoor enthusiasts dependent on devices that require regular charging, this medieval technology offers something profound: a timekeeping system that works indefinitely without power, using only the predictable movement of the sun, a relationship with time based on natural cycles rather than digital displays. 2. The Parchment Map. Your waterproof phone case might protect against a light rain, but medieval travelers carried maps that could be completely submerged and still function perfectly. The Parchment Map wasn't just paper with drawings. It was a sophisticated information system created through a manufacturing process so intense it transformed a natural material into something nearly indestructible. Made from specially prepared animal skin through a weeks-long process involving lime baths, stretching, and specialized finishing, true parchment creates a material with extraordinary durability. The production began with careful selection of animal skins, usually calf, sheep, or goat, with younger animals providing the finest material. After removing hair and flesh, the skin underwent a precise alkaline treatment in lime baths, followed by careful stretching on specialized frames. The material was then meticulously scraped to the perfect thickness and treated with pumice to create an ideal writing surface. But the real genius was in the complete system. The inks used on these maps were equally durable, often made from carbon black, iron gall, or mineral pigments bound with egg whites or tree resins. These formulations created markings that bonded with the parchment at a molecular level, resisting fading and water damage for centuries. Unlike our modern maps that disintegrate in rain or become unreadable when wet, parchment maps could be completely soaked, dried out, and used again without losing any information. Historical accounts describe maps being recovered after shipwrecks, dried out, and used to continue navigation. Try doing that with your smartphone. The most sophisticated versions incorporated multiple information layers that modern cartographers would recognize as remarkably advanced. Some used different inks to show seasonal variations in routes. Others incorporated tactile elements that could be felt in darkness or poor visibility. The finest examples created complete navigational systems that worked in all conditions without requiring any power source beyond human knowledge. For modern travelers dependent on electronic navigation that fails with battery depletion or paper maps that dissolve in rain, this medieval technology offers something valuable: navigation tools that continue functioning in conditions that would render modern alternatives completely useless. A relationship with information based on durability rather than convenience. 3. The bone needle. When your modern sewing kit fails with bent needles and broken threads, consider that medieval travelers carried repair tools that could handle the toughest materials for decades. The bone needle wasn't just a primitive substitute for metal. It was a specifically engineered tool created through a sophisticated manufacturing process that transformed raw material into something with remarkable properties. Using bones from particular animals, often deer or sheep, and specific parts of those bones chosen for their density and grain structure, craftspeople created needles with a unique combination of strength and flexibility. The production process was far more complex than simply sharpening a bone fragment. It began with selecting bones with the appropriate density and straightness, typically the metapodial bones, foot bones, of deer, or the tibia of smaller mammals. These were split along the grain using specialized techniques, then gradually shaped through a series of increasingly fine abrasive stones. The eye of the needle represented particular craftsmanship, created through careful drilling with flint micro drills or through a specialized grooving technique. The final stages involved polishing with progressively finer materials, sometimes including leather with fine clay or ash. The result was a tool with a remarkably smooth surface and precisely shaped point. Unlike our brittle metal needles that snap under pressure, bone needles could flex slightly without breaking, allowing them to handle repairs on the thickest leather, the densest wool, or the toughest hide without failure. A properly crafted bone needle could punch through materials that would destroy modern sewing implements. What made these needles particularly valuable was their versatility across different materials. The same needle could be used for fine fabric repairs or heavy leather work, something modern needles rarely accomplish. The slight flexibility of bone prevented breakage when pushing through tough materials, while the naturally smooth surface allowed easy passage through tightly woven fabrics. Archaeological examples show evidence of repairs on everything from fine fabric to heavy leather, all performed with the same durable implement. Some recovered needles show signs of decades of use while maintaining their functionality. For modern outdoor enthusiasts who face equipment failures in the field, this medieval technology offers something valuable: repair tools that can handle virtually any material with a single implement that lasts for decades, rather than breaking when needed most. A relationship with tools based on durability rather than replaceability. 4. Tallow candle. Modern emergency kits separate light sources, food, and first aid. Medieval travelers combined all three in a single multi-purpose tool. The tallow candle wasn't just for illumination. It was a complete emergency system disguised as a simple light source. Made from carefully rendered animal fat combined with specific herbs and plant fibers, these candles provided reliable light for hours. But that was just the beginning of their functionality. The production process was a sophisticated exercise in resource utilization. Animal fat was carefully rendered to remove impurities, often using specific wood ashes that helped clarify the fat while adding beneficial mineral content. The rendering temperature was precisely controlled to preserve the fat's structural properties while eliminating components that would cause rancidity. Unlike our modern lights that do nothing but illuminate until they die, tallow candles could be partially consumed for emergency nutrition, providing concentrated calories in survival situations. The tallow itself was a dense energy source that could be consumed in survival situations, providing vital fat calories when food was scarce. The real genius was in the additives. Different herbs incorporated into the tallow created candles with medicinal properties. Some included pine resin for respiratory benefits when burned. Others incorporated willow bark for pain relief properties. The most sophisticated versions were essentially portable pharmacies, providing different medicinal benefits depending on whether they were burned, applied topically, or consumed. The wick itself was a product of careful engineering, made from specific plant fibers processed to control burn rate and minimize smoke. Different plants produced different flame characteristics, some brighter, some longer lasting, some more resistant to drafts. Experienced travelers selected wick materials appropriate for their specific needs. Some monastery records describe specialized candles that burned with minimal smoke while releasing aromatic compounds that helped preserve food stored in the same space, adding yet another function to this multi-purpose tool. For modern outdoor enthusiasts carrying separate solutions for light, emergency food, and first aid, this medieval technology offers something valuable: a single resource that serves multiple critical functions while taking up minimal space and weight. A relationship with survival based on integration rather than specialization. 5. The carved spoon. Before Swiss Army knives and titanium camping tools, medieval travelers carried eating implements that secretly contained multiple survival tools in one innocent-looking package. The carved spoon wasn't merely a feeding tool. It was a comprehensive survival system disguised as a simple utensil. Crafted from specifically selected hardwoods like maple, birch, or oak, these weren't just whittled sticks. They were carefully engineered tools created through a sophisticated understanding of wood properties and functional design. The selection of wood was the first critical decision. Different species offered different properties, some more resistant to splitting, others to water absorption, others to flavor transfer. The grain direction was carefully considered, with spoons typically carved so that the grain ran along the length of the handle for maximum strength. Beyond its obvious role as an eating utensil, the handle often incorporated notches and features that served as measuring tools, allowing the user to measure ingredients, assess distances, or even calculate daylight hours through shadow casting. The bowl of the spoon might include specific curve profiles that served as small containers for precise portions or medicine mixing. Look closer at surviving examples, and you'll find that many incorporated hidden features that transform them into complete toolkits. Some handles were designed to serve as fire drills when combined with specific techniques. Others included sharpened edges disguised as decorative elements that could function as small cutting tools when needed. The most sophisticated versions were true survival multi-tools. Some incorporated small compartments in the handle that could store emergency items like fishing line, needles, or tinder material. Others featured specific structural elements that allowed them to be lashed to a stick to create improvised spears or reaching tools. The finest examples could be disassembled to reveal inner components with specialized functions, all while appearing to be simple eating utensils. What made these implements particularly valuable was their inconspicuous nature. While carrying obvious tools might draw unwanted attention in some situations, a simple wooden spoon raised no suspicions, allowing travelers to carry multiple practical tools disguised as an ordinary eating implement. For modern outdoor enthusiasts carrying multiple specialized tools, this medieval technology offers something valuable: a single implement that serves multiple functions while maintaining the appearance of an ordinary object, a relationship with tools based on integration rather than specialization. 6. The sinew of survival. Before paracord and nylon rope, medieval travelers created cordage so strong and versatile it could literally mean the difference between life and death. The medieval cordage system wasn't just about making string. It was a sophisticated engineering discipline that transformed readily available natural materials into one of the most versatile survival resources possible. Rope, strings, and threads were essential materials in medieval life, used in everything from construction and hunting to clothing and tool-making. Medieval cordage engineering began with careful material selection. Plant fibers like nettle, lime bast, hemp, or flax, or animal materials like sinew, rawhide, or horsehair. Each material possessed different properties and required specific processing techniques, such as retting for plant fibers or careful drying for sinew. The processing of plant fibers was particularly sophisticated. After harvesting at precisely the right season, plants would undergo retting, a controlled rotting process that separated the usable fibers from the surrounding plant material. This could be done in streams, ponds, or even with morning dew over several weeks. The timing was critical. Too little retting left fibers difficult to separate, while too much weakened them. Animal sinew, typically harvested from deer or other large game, required careful removal and drying to preserve its strength. The long tendons from the back or legs were particularly prized for their length and strength. After careful cleaning, these would be dried, pounded to separate the fibers, and then moistened slightly before use. The process of transforming these loose fibers into strong rope involved twisting and then braiding or splicing multiple strands together. The direction of twist and the number of strands determined the strength, flexibility, and durability of the final rope. Different types of cordage were made for different purposes, from fine fishing lines to thick construction ropes. The most sophisticated cordage combined different materials for specific properties, such as waterproof outer fibers protecting stronger inner cores, or stretchy sections joined with non-stretching segments for specialized applications. Some ropes were treated with natural waterproofing like pine resin or beeswax for added durability in wet conditions. This skill wasn't just about brute strength, but about a deep understanding of material properties and principles of physics. Good cordage was a force multiplier, essential for lifting weights, setting traps, repairing equipment, and many other vital tasks. For modern outdoor enthusiasts dependent on factory-made cordage with fixed properties, this medieval technology offers something valuable: the ability to create custom cordage with specific properties using only materials found in the natural environment, a relationship with resources based on creation rather than consumption. 7. The living larder. Before refrigeration and canned goods, medieval travelers carried a biotechnology that transformed food while making it last for months or even years. The fermentation system wasn't just about preventing food spoilage. It was a sophisticated biotechnology that transformed raw ingredients, increased their nutritional value, and created complex flavors, all while making food last for extended periods without modern preservation methods. From sauerkraut and pickles that preserved vegetables through winter, to fermented grains for long-lasting breads and beers, or dairy transformed into cheeses and yogurts, medieval people were masters at controlling the action of beneficial microbes. They understood through observation and tradition which conditions favored desired fermentations. The process began with creating the right environment for beneficial microorganisms to thrive, while inhibiting harmful ones. Salt concentration, temperature, acidity, and oxygen exposure were all carefully managed, often using specialized containers designed specifically for fermentation. Clay crocks, wooden barrels, and leather bags were all crafted with features that controlled these variables. The genius was in using natural processes to make food safer, more digestible, and in many cases, more nutritious. Fermentation could neutralize natural toxins, produce vitamins like B complex, and introduce probiotics. Additionally, fermented foods were easier to transport and store, critical advantages for travelers who couldn't carry fresh provisions for their entire journey. Medieval travelers carried specialized starter cultures, often dried on cloth or wooden implements, that could quickly initiate controlled fermentation of newly acquired foods. This allowed them to preserve foraged or hunted food while on journeys, extending their self-sufficiency in any environment. Different regions developed specific fermentation techniques suited to local conditions and available ingredients. Cold northern climates favored lactic acid fermentation for preserving vegetables, while warmer regions developed more alcohol-based preservations. These techniques were carefully guarded and passed down through generations. The most sophisticated practitioners understood how to create sequential fermentations, where one microbial community prepared the way for another, creating complex transformations impossible in a single step. This knowledge was essential for creating certain medicines, specialized foods, and preservation systems for particularly difficult ingredients. For modern outdoor enthusiasts dependent on commercial preserved foods, this medieval technology offers something valuable: the ability to preserve food indefinitely using only natural processes, a relationship with nutrition based on transformation rather than preservation. The forgotten wisdom. We often view medieval people as primitive survivors with crude tools. But their approach to survival wasn't primitive. It was profoundly sophisticated. They created integrated systems where nothing was single purpose. Materials improved with age, and knowledge trumped equipment. While we've gained convenience through modern technology, we've lost something fundamental: the ability to create rather than consume, to maintain rather than replace, to understand rather than operate. Perhaps the most valuable lesson from these forgotten tools isn't any specific technique, but a mindset. One that sees limitations as design parameters rather than obstacles. In an uncertain world, true self-reliance might be the most important medieval skill worth reclaiming.